Right, so today's presentation is divided into 4 different parts. Firstly, we are going to learn how to work with geometry, and then we will talk about how to work with your mesh. Then we will just have a brief review on the theory of linear static analysis and learn about the contacts that are used in linear static analysis. And finally, we'll discuss about the post-processing features and how to view your results, how to generate your tables, and how to generate reports. So before we going to talk about the geometry, let's just have a brief review on what Midas NFX is. And it has 2 different types of modes of application. The first one is the designer mode and the second one is the analyst mode. Designer mode is a much more simplified and it's a geometry based mode of application specifically developed for new users with engineering knowledge but lesser command on software usage, who want to begin with FEA but do not know where to. And analyst mode is for much more experienced and high-end FEA users who have had a higher command and higher control over their FEA knowledge and skills. And the workflow has been designed in such a way that you can perform your analysis very easily. You can learn the workflow very quickly. And you can also perform your analysis in much lesser mouse clicks as compared to the other packages. And it's a very smooth and simplified and a systematic workflow. So even if you make any kind of mistakes during your pre-processing, you can always go back and omit those mistakes very easily. So talking about Midas NFX 2013, the new interface for NFX 13 is much more stable than its predecessor, and it has been designed with the consideration of handling large and complex geometric models, especially when we talk about the large and complex models. When you talk about the lifelike models, let's say large cranes or large industrial structures or large pressure vessels. So as in this particular example on your screens, this assembly was made from more than 1,500 parts, and it was seamlessly imported by Midas NFX. And another ability of Midas NFX is to import different types of CAD models, be it from any popular CAD platform available to you, be it SolidWorks, Pro E, CATIA, Autodesk Inventor, etc. And at the bottom of your screen you can see this box. So these are all the different CAD platforms, CAD software platforms, and the file types, the file formats that are supported by Midas NFX. The preprocessor also allows you to edit your geometry in terms of removing the unwanted holes and the thick fillets around the edges and the corners to help you generate a much better geometry so that you can create a more accurate FE model to obtain better results. And this is a new feature in Midas NFX 2013, which is mid-surface extraction for 2D modeling. So if you have a 3D geometry and which is within the scope of performing analysis using a 2D mesh, you can extract the mid-surface out of those 3D geometries and you can build a 2D mesh on those mid-surfaces and continue with your analysis. So just let us go down to the program again and let's see how the geometry handling works. And let's start by opening a new file. We are using the analyst mode right now. So another thing I'd like to point out is that we cannot create or edit, we cannot create geometry using the designer mode. You can only import our CAD models and we can perform some editing features, some simplification or suppression features on when using the designer mode. Whereas in the analyst mode you have certain options to import your geometry or to create your own geometry or to edit your geometry, use Boolean operations, etc. So we'll be using this model and I'll break it down. We'll break it down into 3 different parts. Right now we'll just create the geometry for this particular bracket model as mentioned over here. This is the project name. And just a short description of what we're going to do here. We're going to perform linear static analysis. So this is the work environment, and here is the geometry ribbon bar. So there are lots of options you see to create 2D point and curve geometry, solid geometries, etc. This is your working grid, and we'll start by creating a box. So we can enter the dimensions in all the three, along all the three coordinates here. So let's use the grid snap and place the base point at the origin. So now we'll create a bracket out of this box, and we're going to see how. First of all, let us move the work plane, and from the selection filter we can choose the face, and you choose this face as our work plane. Go on to a normal view. Now how to modify the size of your grid. To change the least count of your grid, we click on this option called Define Grid, and after clicking on Define Grid, you can enter the least count of your grid size, the width of each box on the grid. So you see now there are much more divisions to work more precisely with the geometry. And now let us create a rectangular profile. Going up to geometry point and curve. We create a rectangle. Choose the option make face. And starting with this as the base point, and right over here as the end point, we have the rectangular profile. If you view it from a different view, you might be able to see it more clearly. So this is the rectangular profile. Now what we're going to do is we're going to use that rectangular profile and cut its way through this box. For that we use the extrude option. Select this rectangular face as the target object, and the global y-axis is the direction of extrusion. Let's take the length as, since we are taking 5 millimeter thickness for the bracket here, and cut its way through. We can also preview our actions before performing those functions, and once we click on apply, you can see that this profile cut all the way through this box, and we can continue further with working with our geometry. Let us delete this rectangular surface since it's no longer required. And now let us divide this solid. So from the geometry ribbon bar, select this solid tab and select the target solid. And we are going to divide this solid using a 3-point plane. So the first point as the base point here, second point in the XY plane along the x-axis, parallel to the x-axis, and third point right over here. And we can also preview the pattern of division of the solid. So you see the solid has been divided in the required pattern. And now this is a needless part, so we can remove it. So this is the crude model of a bracket, and now what we need to do is create 2 holes and punch those holes through this bracket. So we're going to move our work plane to this base face over here. Now we have a grid, so go to the normal view. Now let us create a circle. Now I'm going to show you an alternative way of creating profiles on these solids and extruding them. So first of all, let's create this circle and enter value for the radius of the circle. Click on OK. And now translate the circle along the global y-axis. So by selecting my target object here and selecting the direction as the global y, choose the option copy and enter the required distance and click on OK. Yet right now we created these two circular profiles, but still they are absolutely disassociated with the solid geometry. If we go down to the geometry worktree right over here on the left of your screens, you can see the curve geometries, the solid geometries, and if we hide the curves, you see that the solid is still independent of the presence of those two curves. So how do we take care of this problem? We use this option called Imprint, and taking this as our target face and selecting these two circles as the tool objects, we will imprint these curves on our face. So taking the direction of the shortest path line, and as we click on OK, and on hiding the curves, we can still see the curves are hidden now, and we can see that the imprint has been formed on the solid. Now let us punch these holes through the solid. For that, once again, we will use the extrude option. Choose these two circular profiles, the direction as the global z-axis, length as 5 millimeters, and it's important to reverse the direction here because as we see from the global coordinate system, the positive z direction is in the upward vertical direction, whereas the direction of extrusion is opposite to that. So we have to reverse the direction. Once again, we have to cut through the geometry. So you can always preview before you perform the action. If it seems fine, click on OK. So now we have a model, and this is part of geometry. And another thing I'd like to point out here is I'd like to show you how to extract the mid surface. So to make a mid surface, we choose this option called Make Neutral Sheet, and taking the semi-automatic tab, we select these three faces, preview, and click on OK. So we see that the mid surface has easily been extracted from this model. So now we have a choice. Either we can perform analysis using a 3D mesh, or we can perform analysis using a 2D mesh. Alright, we'll come back to the mesh again. We'll come back to this program again. Let's go back to the presentation. So working with mesh. Now this is in the workflow of Midas NFX, at the top you see the mesh ribbon bar. So creation, assignment of material, assignment of properties, size controls, automatic mesh generation. And then you have a variety of options to create and edit your own mesh, especially creating different types of elements, editing and deleting elements. On the left on the work tree, you have the list of all the mesh sets in your model. And here you have the list of all the properties. So if you're using a model with multiple types of mesh, with multiple types of elements, such as 1D, 2D, 3D elements, or rigid links and other types of special elements, you have a systemized classification of all those properties within your model works tree. So anytime you want to edit any property, you want to change the material, you can easily go down and change the property parameters. So this is the list of elements that are available to you in Midas NFX. The general solid elements, the tetra, penta, and the hexa elements. We also have the pyramid elements in Midas NFX. Pyramid element helps you to generate a hybrid mesh that is consisting of the hexa and the tetra elements, and it can help you considerably reduce the size of your model and provide you faster analyses. For two-dimensional, we have the shell elements, the plane stress elements, plane strain elements, axis symmetric, and also composite shell elements. In one dimension, we have the rod element, the bar element, and the pipe element. And there are some special elements like the spring, the mast, damper, and rigid links, etc. These are some of the mesh editing options in NFX. So as you can see, you can extrude your mesh. You can extrude from a 2D profile to a 3D mesh. You can also project a 2D profile mesh to a particular plane. You can fill 3D elements between two shell meshes, or sometimes if there are problematic nodes, like in this particular case, you can merge them easily. You can sweep the mesh along a profile. You can project the nodes. And especially changing material orientation, it's pretty important when you have orthotropic or anisotropic materials assigned in a model, and where the direction of the material orientation is important. So you can always align the material depending on the need of your analysis. And then the offset feature to extrude 3D profiles out of 2D mesh. And talking about the auto mesher in Midas NFX utilizes multiple cores of your computer to generate mesh more quickly, such that all the different components in this particular model, they are meshed simultaneously. And the auto mesher can also detect areas of geometrical abnormalities or discontinuities, and it can automatically provide you a refined mesh along those types of edges or small holes. And this is just a case study comparison. So you can see in this model with more than 1 million nodes and more than 600,000 elements, the mesh was generated in a mere 54 seconds. So talking about the hybrid mesh, so as I mentioned before, hybrid mesh utilizes 3 types of elements: the tetra, hexa, and the pyramid elements. They're also known as the link elements because they link the tetra and the hexa elements together. And using a hybrid mesh can considerably reduce the size and the scale of your model, as in this particular case, for the same element size, the number of nodes has been reduced to less than half. So it provides you lesser number of nodes, and in turn lesser number of equations to solve, lesser analysis time, without any compromise on the quality of results. And sometimes the mesh may look very fine and very smooth from the outside, but it's very hard to judge the quality of mesh, especially 3D mesh, because the elements inside may not be as good as they look from outside. This is very important, especially in flow analysis, flow simulations, because you need good quality elements with the right amount of skew angle and the aspect ratios. So for that we have a special tool for to check your mesh quality. So this is the dialog box for the mesh quality tool, and depending on whatever mesh parameters you set to decide your mesh quality, you can obtain this set of poor mesh elements. And you can also export this set of poor mesh elements to perform editing features on it separately. So moving back to the program, so you can see we just show you how to use the auto mesher. It has hydral guiders and activate the global coordinate system. So first and foremost, let us use the size control option. So I choose these circular edges and can limit the number of divisions. So I've selected these 4 circular edges, and the aim is to restrict the number of divisions to a certain number, in this case 32 on each edge, so that when I generate the mesh, despite using a larger average element size, the quality of the mesh is preserved along these edges using size control. So now if I click on generate mesh and select the element, and we have an option to check higher order or lower order elements. Higher order elements have nodes on the mid side of the geometry as well. It's mentioned here. And to define your property, you can click on this option. Now there are different types of solid properties. In fact, let us go to the property assignment dialog box. So if you see here, there are different types of properties that we can assign depending on a model. For the 1D property, there are the rod, bar and pipe. For the 2D properties, there are different types of 2D properties available. So for 2D properties, you particularly need a section data, and for the 3D properties, all you need to do is define the material. How to define a material? You can create, there are different types of material models available. So today we are only concerned with the linear static analysis, so we'll talk about linear material data. Typically, to assign linear materials, all we need is 2 main parameters, which are elastic modulus and Poisson's ratio. And mass density needs to be taken into consideration when there is effect of gravity on your system. Let us name it as steel. We can also assign the materials from the material database. So if you see, there are over 1000 different materials available to you in the database with their own properties. And you have a variety of materials to choose from, be it steels, iron, aluminum alloys, silicons, plastics, etc. And so to generate the mesh here, use the high-speed tetra mesher. You can name the mesh set as bracket. So you see, since we limited the mesh size along these edges, we have obtained a much finer mesh, despite the fact we took a larger average element size for the entire mesh. And now let us go back to this surface model that we have, and let's hide all meshes. So yeah. So on this model, how to generate a 2D mesh, let us assign a 2D property first. We'll use the material as steel and enter the thickness value. Since we are using a 2D mesh, so we have to assume the thickness values, and we are taking the assumptions that the deformations acting along this thickness of the 2D mesh are infinitesimal as compared to the lateral direction, and we click on OK to assign the 2D property. Now we can generate. Once again, we'll use size control for the edges, selecting these two edges. We'll restrict the number of divisions to 32 and click on OK. So let us generate the 2D mesh now. And select all these faces together. Let us use a triangular plus squad elements and take higher order elements into consideration and enter the mesh set as bracket in 2D. So we have obtained our mesh. For the moment, let's just concentrate on the 3D mesh that we'll come back to, and let's go to the slideshow. So talking about the linear static analysis, it is the foundation of any type of analysis that we perform. Even if we perform nonlinear analysis or dynamic analysis, linear static analysis is considered to be the primary form of solution for approaching any engineering problem. And it's basically derived from two terms, linear and static. Linear is basically the material model, which obeys the proportionality law given by Robert Hooke, the Hooke's law that we popularly call as. And static determines the time-independent characteristics rather. So whatever assumptions that we are taking in a model, they tend to be constant with time. All the boundary conditions or the loading conditions, the material conditions, they are assumed to be constant with respect to time. And what you see on your left here, this is the governing equation of linear static analysis, which is F is given by Ku, where K is the stiffness matrix and U is the displacement. And this equation is obtained from the material curve you see on your right, and this particular zone bounded by the red box. This is the elastic region for the material, the point till the yielding point, where the stresses and the strain increase proportionally, and are equated by this factor E called modulus of elasticity, which is a characteristic of every material. And this is the main equation, the stress strain equation, which is transformed into the governing Hooke's law equation that we use for our convergence. If you see the rest of this zone over here, this is the area where the material stops obeying the linearity and where it starts its nonlinear behavior. If you missed out on the nonlinear analysis webinar, you can always send in a request to us and we will send you the recording of the webinar soon. Now, as I showed you the material dialog box, so there are different types of material parameters that we can enter. We can directly enter from the database, or if we have our own experimental material data, then we can create our own custom material. Similarly, the safety factor data, if you're designing for safety, so there might be some safe values of stresses for safe design. And if we are performing thermal stress analysis, then we need the coefficient of thermal expansion. Now, the different types of boundary conditions that are used, the fixed constraint, the pinned constraint, and the symmetry constraint. In fixed constraint, all the degrees of freedom are restricted for a particular node. For the pinned constraint, only the translational degrees of freedom are restricted for the node. And the special type of constraint is the symmetry, in which we assume the model to be symmetrical with respect to a particular plane. And it's symmetrical in terms of its geometry, in terms of its mesh, and in terms of the loads and the boundary conditions applied to it. So let's say if a model is symmetrical in terms of geometry and mesh, and yet the loads acting on it are not symmetrical, then it is not advisable to use symmetric constraint. Then axisymmetric constraints are required. So anyway, this symmetric constraint helps us to reduce the scale of our model, especially if we have very large models and which have symmetrical geometry and loading conditions. We can reduce the scale of model to, let's say, 1/2, 1/4, or 1/8, depending on the type of model, and in turn we have lesser amount of elements to solve, and we can save a lot of time in our analysis. Now, these are the static loads that are used in minus NFX, all the different types. So right from gravity to the translational displacement or the linear force, rotational displacement or torque, pressure, remote load. Remote load is a case where the point of application of load does not lie on the geometry or on the mesh. So we can assign a remote loading location and enter our load values to the dependent areas where the load is acting. The bolt load, this is for assigning the bolts in your model. There is no particular need to model the bolts separately. And then we have the bearing load. The major difference between the normal concentrated force and the bearing load is that along these curved profiles, it will act as if a bearing, it will transfer the load radially rather than linearly, as in case of the concentrated force. And now we talk about contact. So in general, what is a contact? It is it is a way to transfer load between two separate mesh sets in contact. So if there are, let's say, different mesh sets and there is no nodal connectivity between those mesh sets, yet in physical phenomena the load transfer is taking place between those two bodies. So we need to assign the contact between them, and depending on what kind of contact is taking place, we have two types of classifications of contacts, the linear contact and the non-linear contact. So in linear contact, we have the sliding, bidirectional sliding, and the bonded contact, the welded contact. In welded contact, there is no separation under any circumstances, be it horizontally or vertically. In bidirectional sliding contact, there is no separation in the vertical direction, yet the mesh sets are free to slide along the horizontal direction. In nonlinear contacts, we have the rough contact and the general contact, where there is no sliding but a possibility of separation in the rough contact, whereas in general contact there is freedom for the mesh sets to be in contact in any way possible, be it sliding or separation. Another special contact, it's another type of linear contact, which is we call in NFX as the breaking weld contact, which is nothing but the welded or the bonded contact with a certain breakage force defined. So if the load values reach a certain value, the contact can separate between the two mesh sets. This is just an example of the different contact types. So if we zoom in over here, if you view very closely, this is the welded contact. So you see the nodes are connected with each other and there is no movement. In the bidirectional sliding contact, there is some movement. You can see the separation between the nodes. This is an example of the rough contact. In rough contact, where there is contact separation but no sliding taking place, and the general contact where sliding as well as vertical separation is taking place at the same time. So let's go back to the program. Now this is the model that we were working on earlier, and now let's assign some loads and boundary conditions to this model. So first of all, we'll assign some constraints. So selecting these two faces, we can apply the pinned constraint. And similarly, we'll assign this pressure on this face. So we are applying normal pressure, which is uniformly distributed all along this face. Center value of 1500 Newton per millimeter square, and we can preview, click on OK. So now we have assigned the loads and constraints. All we need to do is create an analysis case. Go to analysis, click on general. Today we are going to perform linear static analysis. If you want to learn more about other analysis, you can sign into the other webinars that we will be conducting over the course of few weeks. And let us solve the model. Over here at the bottom, you can see the number of nodes and elements in your project. So it has 47,000 nodes and 28,000 elements. And we just wait for the solution to converge. You can track the progress of your analysis over here at the bottom on the output window. So we can obtain the simultaneous progress of the model. So while we obtain our results, you can see here on the left side of your screens the model works tree and the properties window at the bottom. And as we speak, we obtain the results. So you can view the different types of results obtained to you. And these are these solid stresses, the von Mises stresses. These are the translation. So you can view them in different edge types. And you can also compare with the initial shape. The animation can be viewed and you can obtain the minimum and maximum values of the stresses. And of the translation taking place. If you want to insert any other types of results, you can always select them. Reaction forces, let's say. So we obtain the reaction forces here. And we can use the probe tool to view the results on each node, on individual nodes. So it's a very convenient tool to view node results, especially in the critical zones. And using the clipping plane tool, you can slice your model along any section, along any plane. You can view results from the inside. This tool is pretty useful for thermal and heat flow analysis and other CFD flow analysis as well. And the isosurface option, which provides you the results only above or below a particular limiting value. So in this case, the limiting value is 1351, so we can only view the results above that particular value, or if we choose lower part, we'll only obtain the results that are lower than this limiting value. Alright, so let us save this file as another name, and we will now perform the analysis on the 2D mesh that we generated. Remove this analysis case and let us concentrate on the 2D mesh that we generated. So first of all, let us assign the constraints again along the edge. These two edges, fixed constraint here, and pressure along this face, pressure of 2500 newtons. So the pressure has been assigned. Now we can create the analysis case. So if you see here, once again we'll just you can always go back to the worktree and create a different load set. So let's name this constraint set as 2D constraint. And similarly rename this one as 2D load, this load set. So this is why it's good to make your workflow as systematic as possible, so that if you perform any sorts of mistakes or omissions during the course of your analysis, you can always go back and correct them. Now let us create the analysis case. And from the active sets, let us only select the 2D mesh, the 2D constraints, and the 2D load set. Name the analysis case as case 2. So this is the 2D case. You click on OK. And now we can solve the model and we obtain our results. So 3 typical types of shell stresses, the total translation. And going back into the model worktree, if we activate the 2D property, so we can see that our model is as good as that 3D model we created a while ago, and it saves us a lot of analysis time. So now let us talk about how to, let's say, assign contacts in your model. So I'm going to open this file called contact. Now there are some loads and constraints already acting on this model, and we will create 4 different types of contact types. Firstly, let us go to manual contact and choose surface to surface contact, welded contact. And as we see, there are 2 mesh sets. So for the master, let us select these mesh sets, and for the slave, let us select the upper mesh set and name the contact as welded and click on OK. Oh, pardon me. Right, once again let's do it. For the slave phase, let us select these upper elements and name the contact type as welded. Let's click on OK. So if we go to the contact in the worktree, we can see the contact definition. This phase in contact. Now similarly, We'll assign more contact types. So now let us choose the bidirectional sliding contact and follow the same procedure. Select the master face. And then select the slave face. Let's name this as sliding and click on OK. Now third contact type as the rough contact, or let us just concentrate on these two contact types, since rough and the other type of contact, they are nonlinear contacts, so we'll have to refer to the nonlinear analysis theory. And let us assign the analysis cases. So we have the mesh sets, we have the loads and boundary conditions. Let us create an analysis case. So let us create the first analysis case with just the welded contact. Let us name it as welded. You can again go and edit, and we can see that we kept only the welded contact here in this particular case. And similarly, create another analysis case, name it as sliding, and we will only retain the sliding contact in this case. Same boundary conditions, same types of loads acting, only the differences in the contact types. Now let us solve our model. So we obtain our results. Let us look at the edge type, and we can see the difference in the movement of nodes. So you see the translations here, there is a displacement of the nodes here, whereas in the bonded contact, in the welded contact, there was no relative movement between the nodes. However, there is no separation taking place in either of the contact types. So let us move back to our presentation now. The Midas NFX provides you a very convenient method to define your contacts in model. So if you have very large assemblies and all of them need to be assigned a welded contact, you can just click on one button and automatically the contact will be assigned between those geometries. And now we talk about the post-processing. So we already saw some sophisticated post-processing functions, and this is the results toolbar, different types of contours and other advanced post-processing options such as result calculation, viewing the results on curve, etc. Now when you have nonlinear analysis in this on the screen, you can see an example of a nonlinear explicit analysis. So you can see all the steps and the increments during the course of your analysis and the intermittent results that you've obtained. On the right is a legend which shows you the distribution of the contour and what numerical values are corresponding to those contours. Now the different types of contours that you can see, the mesh shape or the transparent shading, or the line contour or the discontinuous contour. So the numerical values of results that you obtain, they can be easily exported into Microsoft Excel, and you can also generate automatic reports which can be exported to Microsoft Word. These are some post-processing options, such as the clipping plane tool. Like mentioned before, it's very important when it comes to flow simulations and heat transfer analysis. The vector plot, and you can, for large assemblies, you can also view the results in post-processing for individual parts of your assembly. And these are some special post-processing functions for flow analysis, for CFD analysis, such as the streamlines and the mesh deformation function. And these are the new post-processing functions that have been incorporated in Midas NFX. So on the left you can see the element contour plot. So it enables you to view the results for the different types of elements simultaneously. Earlier that wasn't a possibility in Midas NFX 2012. And on the right you can see the results for composite materials. You can view the results by the global ply ID and view the results along the thickness of the laminates. So that's it for today's presentation. And if you have any kinds of questions and queries, please type them down on the chat window. And at the end of this presentation, you will have a survey form. So please be kind enough to fill that survey form for us, and it will help us serve you better in the future. If you want to request for a trial, or if you want any kind of queries about the software, please write into us. My email ID is apoor@midasit.com, and you can also write into my co-workers, cyprian@midasit.com and piotr.stepian@midasit.com. So if you have any questions or queries regarding the software, any request, if you want to download the trial, if you want a trial extension in an exceptional case, you can always write into us. So anyway, I would like to thank you all for coming out tonight. Thank you for sparing your time. And from the entire Midas NFX team here in South Korea, very goodbye. Thank you. Right. Done.
Very good.